This conference will now be recorded.
And we're now being recorded. Very good. So we're about to take a look at the Eagle Ray baseline 4.1 modifications generated by a small group in Nepal using some tools that we don't typically use, a lot of computational fluid dynamics and some simulations. And we're moving forward towards a vehicle that has a proper planform and airfoil stack that allows it to have a 3-point takeoff and landing. We haven't yet done detailed analysis of how well it's going to perform at altitude. We've looked at a couple different altitudes and some different configurations and speeds. And what I think we're going to do is just have the Nepal team present their changes, their recommended changes to Mark Page, along with their analysis of how the changes affect performance. And we'll get some real-time feedback from Mark and others that are on the chat. And then afterwards, Mark's going to have a couple of weeks to take a look at it and decide what we want to accept, what we're not going to accept, and if there's additional changes that need to be made before we go forward and close this out and move it over to full CAD and proceed with design of all the internal structures. So with that, I'm going to turn it over to Sudip and Bikalpa. Go ahead and just introduce yourself a little bit before you get started.
Thanks, Ron. Hi, everyone. So today, it will actually be 3 of us who will be presenting our parts. It will be Ashish as well, who's gonna, I think, so Ashish did a lot of the dynamic tests, so I think it's only fair that he talks a little bit about that. And so I'll start with the presentation, and Ron, I hope it's okay that I'll go through the introduction as we go through the slides. I have like an intro page there, so right, I'll start sharing my screen. Can everyone see my screen, the entire thing?
Yes.
And the slide now as well, right?
Yep. See him now.
Okay, it seems like it's a bit laggy. And this go-to meeting thing is exactly on the where I don't want it to be in that window. Collapse? Yeah, all right. I think that's better. All right. So the design we're going to present today was done by our team at the Institute of Engineering in Nepal. And let me introduce the team. So there's 2 interns that are working with Ron and the KWF team at the moment. So that is directly what the KWF's AI team is doing and other work. Ashish, who is also going to be presenting today, is a graduate student. I think Ashish will introduce himself in more details later on. And he's actually evaluating our UAVs, and Ashish particularly is working on a different high altitude platform, UAV platform, as part of his master's thesis. The 4 guys here, Akash, Abhishek, Anurag, and Hem, they are working on Eagle Ray as part of the undergraduate thesis. And although I won't get to present those work directly in the presentation today, a lot of what they are doing is building up to, sort of, I think, what we are going to be able to present in the next several months. So that'll be like a completely different set of work that'll come out of their thesis. So similarly, there's Tan, who's also working with us as part of the team, and then Kamal is a faculty member at the Institute of Engineering, Pulchok. He's also a faculty member for aerospace engineering. Bikalpa particularly has a really good experience with aerospace operations and aviation, and also with his recent background in optimization, aerodynamic optimization, he has actually been a very central part of our team now. And myself, also an assistant professor at the Institute of Engineering. My research background particularly is in experimental and numerical hypersonics. But since I can't just start building a shock tunnel here in Nepal yet, we are starting with UAVs, and I think that'll actually serve the local purpose in Nepal. It's in a more suitable way and more contextual way. But hopefully, we'll build scramjets in the future. All right. So I'll talk briefly about methods. All right. So what we have done is there's a couple of tools we are familiar with. We have been using XFLR5 for a very long time in Nepal as part of our teaching as well. And CFD is quite common for us to work on these days. Although initially we did CFD just to check how off or close the CLCD values would be. A lot of the results I'll be presenting today relies more on analytical quick tools. So OpenVSP is the platform we use to finally provide the design and the exact parameters that we have in common. On simulation side, particularly flight simulation, we work on something called the X-plane. We design the airplane within that module. It has the design module that X-plane has, which is called Plane Maker, is not extremely precise, just like VSP or XFLR5, but it does its job. It's based on something called a grid element model. So the shape itself does not matter. Whatever you have inside the panel matters. So when we had this issue of trying to change a lot of the design parameters at the same time and come up with quick answers, we realized we could not really give it time to do every piece at a time, every value at a time. So what Bikalpa and Anurag and others did, Akash as well, I think, and Abhishek, so they worked on SU2, which is an optimizer. But since it's very, very expensive, we worked on Aeolus, which is more analytical and quick in nature. But like I said, what will come out of Anurag, Akash, and others' work will be good optimization, high fidelity optimization done in SU2. So the optimization that we relied on, we took it a lot of it at face value, but it's going to come out of it's low fidelity. And then we reevaluate those changes in other platforms. All right, so I'm going to hand this over to Bikalpa, and Bikalpa is going to let me know when to change the slides. Bikalpa, it's yours now.
Yes, thank you, Sudip. Hello, everyone. My name is Bikalpa, and I have been, so my past experience, I had been working as a flight operations engineer in Bhattarai. So it was about 6 years that I worked for the airlines. And after that, I recently moved on to academic section side, and I just did my master's, and I just completed my master's this year. And a part of my project during my master's was to run the optimization in SU2. It was basically for even smaller vehicles, such as micro air vehicles. So it was the optimization of micro air vehicles that I was working on in my master's project. So for this, so I'll now proceed with the presentation. So as Sudip said, so the objective of is okay. So I'm continuing. Someone got okay. Anyways. So okay. So the objective that we selected for the optimization was to improve the efficiency, and we took twist, dihedral, and sweep as the variables that would affect this efficiency factors, and we did not limit. We did not do any constraints. We did not put any constraints for the optimizations, and also we did not want to change the total plan form, whatever was initially. So we did not change the span length, and we did not touch on the airfoil chord length and everything. So basically we use the optimization tool, that is Aeolus. It's very much similar to OpenVSP, but it has integrated optimization algorithm. So both the options are there, either to use gradient based or gradient free. So for our case, we use gradient based optimization, and the aerodynamic analysis was done with 3D panel method. So also because most of the analysis in OpenVSP were done with vertex lattice method, and there was some discrepancy with the 3D panel method, the results that we got from Aeolus and from the OpenVSP. So whatever design we got after optimization in Aeolus, we loaded that design back to OpenVSP, and all the post-processing was done in OpenVSP. So we can go to the next slide. Yeah, so this is the basic isometric view overview of the changes that can be seen in the baseline and the optimized wing. Baseline is named design 3, and the optimized result is named as 4.1. So basically, the major changes maybe you can notice from here is the tip diameter. It's swept in a downward direction just to accommodate the landing gear at the tip. And we'll see more details on the front view, top view, and orthogonal views. Can we go and move into another slide? I can't see the slide change.
There's a bit of a lag, unfortunately, Bikalpa. Can you see it now?
No.
I can get some more. I got plenty.
Yeah, I see it just fine.
Okay, so just now it loaded for me. Yeah. So now this is the orthogonal view. We have a top view, side view, and front view, so that we can make a clear assumption of how the wing looks like. So basically, from top view, we can see that slightly sweep has changed at the nearing the tip. It has moved slightly upwards, and on the side view, it's shown only. We can't see the twist distribution in the side view, but at least we can see how the wing tip is directed on downward direction. And in terms of dihedral, there is a slight change near the section where there is a connection between the wing and the body part. But apart from that, dihedral remains almost the same. Can we move on to the next slide? So on the next slide, I'm going to talk about what was the overall effect that was brought through with these changes. Okay, so we could not see very clearly what was the changes in the twist angle in the top view and the side views. So here is a picture of twist distribution, relative twist distribution for baseline wing, that is design 3, and the optimized wing. So for the optimized wing, what we see is now the washout. So washout, what was present there initially has been now decreased, and we are getting a lesser negative twist at the tip area. So that is causing the wing tips to generate more lift when the wing is at a relatively same angle of attack as the baseline wing. So now we have a more distributed lift throughout the wing. Initially, it was more concentrated on the wing body section. So as a result, what we have is at the same angle of attack for design 4.1, we have higher lift. So there is a shift of CL versus alpha curve. So what this translates to is when we look at the landing takeoff distance, because now we have a higher CL at a similar angle of attack, that is around 6 degrees angle of attack, we have higher CL. So basically we were able to take off within a shorter takeoff distance. And also because of the lift distribution, if we see at the CL versus CD curve, we can see that the total drag for the optimized wing has been reduced slightly, especially it's observed after CL is higher than 0.5. And this is basically due to the reduction in the induced drag, because parasite drag, it's overall almost the same, because we have not made any significant changes to the weighted area. So overall,
Bikalpa,
Yes, yes, sir.
Yeah, just a quick question. So
Yes.
these, with the changes, you've preserved the trim. So the pitching moment's been trimmed out at the nominal design lift coefficient. Is that the case in the optimization? So it was optimizing both for efficiency, but also while respecting trim. Is that true?
Uh, no, actually, for the during the optimization, initially we had left the constant. We didn't have any constant during the optimization actually.
Okay. Okay, cool. And that's something I want to learn more about, but this is interesting. Carry on. Thank you.
Yeah, thank you. So yeah, so now as a result of reduced induced drag, what we can see is there is a, although it's a very marginal difference, but we see there is a increase in CL by CD ratio, maximum CL by CD ratio for the optimized wing, and that is occurring around CL equals to 0.6. And now also when we look at the leading edge moment, we can see that with the new design, we have the slope of the CL versus CM leading edge. We have a steeper slope for the optimized wing, so that translates to, I think, higher static stability. And also with the optimized wing, we see that the center of pressure and the aerodynamic center has moved slightly upward, and although the volumetric center of gravity has moved by around 1 inch, the aerodynamic center has moved by around 3 or 4 inches. So that way we are now able to have a larger static margin with respect to pitch stability. So from here on, I think Mr. Assis is going to present whatever was done for the stability analysis.
Okay. Hello, can you hear me?
Yes. Yes, Assis. Yes.
Hello, everyone. My name is Assis Kargi. So I'm currently studying my master's in the same university. So I'm also involved in some designing some other UAVs as well. So in this Eagle Ray project, so I have been I've been generating some results in terms of these plots and graphs. So using different platforms as mentioned earlier. So this slide shows the pitch, directional, and roll stability for the baseline 4 version. So the pitch stability, the coefficient of pitching moment is plotted, and then it is seen that the coefficient of pitching moment, that is CM, is positive for positive angle of attack, and so that it's longitudinally unstable. So but then the directional and roll stability seems fine, so they are stable. Next slide, please. Okay, so this is the dynamic analysis result. So in longitudinal direction, we studied the phugoid and short period excitation. So these graphs are the time response to phugoid and short period excitation. So the green curve here is the angle of attack variation with time, and then the black curve here is the pitch angle variation with time. So when left for phugoid oscillations, so the disturbances was found to be damped within about 3 minutes time. So under the, but then the short period excitation, so it damped out within a second pretty fast. And also to add to this, so these tests were done under the angle of attack of 10 degree. As beyond that, the baseline flow entered the stall region. So next slide, please. So this curve shows the dodge roll tendency of the aircraft, the side slip angle variation with the time. So the dodge roll is again excited. Dodge roll mode is again excited through the rudder doublet input through the control stick. So when left for dodge roll oscillation, the aircraft before returning to equilibrium, it oscillated about 5 to 6 cycles for 6 minutes of time. So after that, it returned to 0 side slip angle. So that's all for stability analysis. And on next slide, so this is, so next slide please. And so this is a simple calculation, and then to calculate the maximum velocity possible, maximum possible velocity at cruise. So we calculated the required power variation with altitude. So it is not that significant. So also you can see here that the with available power of about 850 watts, we get the maximum velocity of 45 meter per second. So we also performed this test in explain flight simulation. So the velocity there was also quite close to this velocity value. So we consider the density variation from mean sea level. So that is, okay, there is a typo there, it's MSL, mean sea level. So we consider the density variation of mean sea level to 10,000 feet of altitude. So this is to calculate the maximum velocity. Thank you. That's all from my side. Thank you, sir.
Okay, thank you, Ashish and Vikalpa. All right, so I'm going to move on to talk about flight tests. And just before I do that, I want to mention Ron emailed me about an hour or two ago mentioning that I have been mixing my units. So mostly we do work with SI units, but depending on software, we do get lazy trying to convert between when you're working within platforms. So we very rarely use our Freedom units. So it's mostly just SI. So I think if any of you were confused about this CMLE plot and the plot we have here. So when I move to flight test, I want to mention we moved the center of gravity to match whatever takeoff performance we wanted and eventually the flight performance, right? So the center of gravity, whatever we had from VSP was a volumetric center of gravity. And so now the center of gravity has been moved aft quite a lot. So that makes the aircraft, in a theoretical sense, unstable, right? And so if you just look at the details here, we have a needle point about 700 millimeters. Here, luckily, we just have the C units. And then, so the location of center of gravity, I've given a range here, although I put my defaults at 855 millimeters from the leading edge of the new aircraft. And that kind of applied this stability criteria or this flying criteria for center of gravity applied to baseline 3 as well because I think last month when we were presenting purely from baseline 3 perspective. And so for that one, we were about, if I remember my Freedom units again, it'll be about 10 inches forward from where we have now. And so the takeoff speed is about 26 meters per second, which is better than what it was before. So I wanted to get to about 20, but I could not do that. And so from XFLR 5, if you just look at that data for baseline 3, it would be about more than 23 meters per second to get a vertical acceleration at about 8-degree angle of attack. So with the current model, we take off at about 9 degrees of angle of attack, which includes your 6.3 degree of default angle of attack plus 3.1 degrees of angle of attack maintained by the landing gear position or the landing gear difference in height. And so we take the aircraft to slough, which is steady leveled unaccelerated flight, and we test all these performance. And so we could get slough conditions between 28 meters per second to 36 meters per second between flight level 10 and 20. So I think the maximum altitude that we cruised at was about flight level 50. And it was the rate of climb is not that high. We climb at about vertical gradient about 3 degrees. But I'll show you that performance shortly. So when you talk about takeoff run, so it takes about 1,000 feet, which still is a bit disappointing since we think about taking off from a runway in Nepal, but with a more powerful engine, we can easily, hopefully, overcome this. Right now, the engine is relatively, mild in power because we just want to test at low speed ranges. And so takeoff speed is about 50 plus minus 2 knots indicated airspeed. I think it's about 52, somewhere around there. And then the velocity, as you can see, it takes up at about 1,000 feet, or just after that. And so that's where we take off, right? And so to show a basic flight characteristic, I think I want to close with recorded simulation, as I was showing, I think in my presentation about a month ago. So I think what the final point when I show this is, so there was one part where we looked at, so what Bikalpa was especially presenting on earlier, was we were looking at how do we increase the basic performance parameters like CL, how do we decrease CD, how do we increase lift to drag ratio. Then we take it into another round, which is how do we actually make the airplane fly the way we want it to. And I think that second part is very relative in nature. It depends, I think, a lot on what from our side is a good flying airplane, and that might be completely different from what you might think is a good flying airplane answer. And so I'll just show you me flying this airplane. So that's what you just looked at, is the motion of elevons. So these control surfaces are both ailerons and elevators. And so we have rudders down here, which I'll move shortly. And then we start the engine. It does not swirl when we are on the runway, so that's good, because typically that can be a problem. So it's very steady on the ground. That's partly to do with how we put the landing gear as well. And then I trim the elevons to about 0.6, and then the aircraft flies at about 52 knots. And then I do some test of maneuver shortly. You can see it actually swings left and right a lot. So that's somehow, I guess, the characteristic of its Dutch roll characteristics. But still, it's so this is just me trying out random maneuvers. And then I am immediately back to land. And then just above about 55 knots indicated airspeed, you can touch down. And so I think that closes my part of the presentation as well. And I think in the end, I just want to make the point that, went through the part that Bikalpa was presenting about. And then, so that's just talking about how you change the planform to increase basic performance parameter. And then the second phase was to look at, what airplane flies better, what center of gravity position is good for us. And so, I hope we have been able to explain these two parts clearly enough. And Ron, that would be the end of my presentation. I'm going to leave.
Sudip, I have a quick question. Could you go to the slide that shows the planform comparison of 3 versus 4? X-Plane is wonderful, isn't it? I love that thing. X-Plane is amazing. Such a useful tool.
Nice. Yeah.
Okay, so if you were to okay, I'm looking at I'm looking at 4.1 planform. Could you tell me where you were flying your CG at? Just put your cursor about where the CG was on the airplane that you found that you needed to get the airplane to fly well. If
just where my cursor is.
Okay, right about there. Okay, cool.
Can you see
that? Yeah. Yes, I do. Thank you. That's exactly what I was curious about. That might be a consequence of the extra sweep. I think the lower sweep helps keep the flyable CG closer to the centroid of the center body. So that's just something that might be a consequence of the extra sweep, which does add stability, but then it also asks the payload to shear aft. Now, we could keep the sweep, and I know you guys have been largely preserving the planform, but My instincts would be that if we really like the extra sweep, we might need to shear the center body aft a little bit. Leave the wings where they are. Just imagine sliding the middle airfoil back to move the centroid of the volume closer to the target CG, so that we'll have a little less leading edge sweep, a little bit more of a trailing edge sweep, and then I think everything could line up nicely where the usable volume and the flyable CG are well aligned. So, but those are all easy. Those are logical steps. That's something in the big airplanes, like if you're doing a 777 or something, you design it, you fly it around. The aerodynamic CG does not line up with the real CG. So then we slide the fuselage. We just slide the fuselage on the wing until the two line up. It's a real simple process. And it turns out you often don't have to slide the fuselage a lot, just a little bit, and it'll get those things lined up nicely. So describe to me a little bit your experiences hand flying the airplane. You said you could really see the Dutch roll. It was, and it looked like it was taking, what was it, like 3 cycles to half amplitude or something, which is pretty lightly damped.
Yep.
Dutch roll is often lightly damped. Pitch damping looked awesome. And the Fugoid, of course, is going to, if it's a clean airplane, it's going to be that way. How else did you find the airplane handled when you were landing? Did you have any bobble issues bouncing up and down with the wheels set to liftoff attitude? Did it tend to pop back up in the air and then land and pop back up?
Yeah, so with the angle of attack, right? Like typically we are at a high angle of attack even when we're cruising. And so when you approach to land, I sort of pitch up to not stall, or to maintain the lift. And I also want to decrease the speed. And so I keep pitching up, but unfortunately the landing gear, the nose landing gear is still so tall that I tend to touch down with nose landing gear first. And so that was one problem that was a bit hard for me to avoid. And then the other one was, I think I became a relatively good pilot to fly Eagle Ray. So, but when I was flying baseline 3 last month, I would always bounce, like almost every time. It's possible that I've kind of learned how to not bounce while flying this version.
Yeah.
But landing has become relatively simple so far.
Good. So something that
just approaching
you might yes, something that is a consideration. I mean, a long time ago, I experimented with a landing gear that was just had a little spring to retract it. But I rigged the gear forward, so it was sitting on the ground. The weight held the gear extended against a stop. Then after I lifted off, it just automatically retracted. No servos, no nothing. It just spring-loaded, retracted. And in this case, when you come in for landing, it'd be kind of nice to let the nose go to the ground and just come to a stop instead of touch the nose wheel and bounce back up. It might be pretty nice to derotate the airplane. So depending upon where the turret is and so forth, that might be a kind of a fun little easy, low-cost trick we could do. The other thing too, on the rolling takeoff, it is a lot of distance for rolling takeoff. Normally an airplane like this would be catapult launched. So I had a question, Ron, is because 1,000 feet is a lot, obviously, and one thing that's really cool about little catapults is that you always know where you're going to take off. You don't always know where you're going to land. So if you can land without a net, that's cool. If you can land on a runway, that's cool. But for takeoff, you really could get away with a little catapult assist, whether it's a little pneumatic catapult or something. What's the thinking on that these days?
Yeah, hi, Mark. I'm not opposed to having a catapult if it's can be made relatively portable and lightweight. I'm also thinking in terms of possibly a sled as opposed to a catapult. We'll get a little bit longer takeoff distance, but still controllable.
Yes, you bet. And it could even be just even bungees are pretty effective. Although this what's the gross weight of the airplane right now? Is it like 45 pounds still?
Yeah, I think it's around 45 to 48 pounds.
Okay, so that's a lot of
we
airplane.
had
So
set it to about,
say one more time, Sudip.
we set in most of our tests 2 kilograms. And I think
I couldn't quite make that out. I was getting a little interference, but I think the one thing with a catapult is it's always an option. You know, you don't have to, you know, you can leave that even as a decision for later if you say, hey, we found a nice little catapult we like, that's inexpensive. I think that the guys at, what is it? What's that place called? UAV Factory. UAV Factory has a little pneumatic catapult we like a lot. It's pretty lightweight. So that's a possibility too. But and one more question, Sudip, on the flying qualities. So the Dutch roll, would you say that that's the biggest nuisance while you were flying? In other words, you're still on mute, Sudip. In terms of your ability to make the airplane perform the way you want, was a Dutch roll the biggest thing you were noticing as an issue?
so the Dutch roll was always there when I was flying, particularly when taking off and maneuvering to land. You always notice that. But it did not bother me to trim it to, for example, cruise to a particular position or like when I turn. But yeah, it's always there, and you know, in my mind, I always thought if there's a camera there, then that's going to struggle a lot.
Yeah. So one thing you could
focus
do
on.
also, yes, in X-Plane, it will let you put a little auto flight control thing. You probably know this. You can put a little yaw damper in, and you just tell it how many degrees of rudder per degree per second of yaw rate. And you might just play with that a little and see if it makes the airplane fly right. That'd be a good indication that the Autopilot should be able to handle it nicely. My guess is that it will be able to, but sometimes, depending upon where the rudders live, sometimes the rudders make their own rolling moment, and then you find it's more challenging to get what you want, and you have to get aileron in the picture too. But I'm pretty optimistic that with rudder damping, even an old school radio control simple rate gyro damper that's not even in the Autopilot, just outside, would probably be a nice feature on the airplane. But it also sounds like you were able to control heading overall, even though you had the ringing, and you could line it up well. You could control it well enough to set up for a landing and execute a landing.
Yeah, after a bit of a practice, it was okay.
Yes, great. So guys, is it okay if I just ask a bunch of questions, or was there another presentation we wanted to get to?
No, at this point, Mark, go ahead and ask your questions so you get as much information as you can. You're going to need.
Okay, cool. So tell me about the down winglets are cool because they give you can integrate landing gear and things like that. Was the up versus down winglet, was that part of the gain, the lift to drag ratio improvement that you saw? Was that playing much of a role?
Yeah, we did test both wingtips down and up, but we didn't really see much of the difference in the lift to drag ratio because of the wingtips.
Okay.
Bikalpa, so do you want to talk briefly?
Yes.
So I think there was something Bikalpa had found with related to wingtips. Do you want to talk about that, Bikalpa, without the sweep? We did not include that in the slides.
Yeah, definitely. Yeah, definitely. So one thing I wanted to ask Mark was the way the wingtip was swept backward. So was there any specific reason so for which we had the wingtip to be swept in such angle?
So if we go back to the image we were looking at before, comparing 3 and so I'm trying to remember. So the winglet appears quite a bit bigger than. Sorry, wait a minute. Let's see here. Let's go back. Okay, good. Actually, let's go up a slide to 5. There we go. So I'm trying to remember, Ron, if I had the winglet swept that much, or if that happened after I put together the initial package. I honestly don't recall. It does look like a lot. It looks like too much. I agree. The there will be a point at which the wingtip sweep will, of course, work against you, because even though you're increasing lever arm, you're losing lift curve slope because the sweep is going up so high.
Yeah,
And then elastically, so the short answer is that the winglet, at least when I first looked at the problem, was sized to get a certain level of directional stability. And it looks like you guys may have matched it. I think 0.018 or something, CN beta, or 0.01, between 0.01 and 0.18 is what I typically target. If I have to live with 0.01, I will. If I can get 0.18, I'll shoot for that. But so no, there are, to me, that's an open degree of freedom. It can be unswept, and you could take a look and see what that does for you. It'll unswept from what it is now, not necessarily zero sweep.
Yeah. So while we did run the optimization simulation, so it was trying to basically get the sweep back to 0. So that way we had a relatively, if you see that the wingtip was typically rotated in the up to 90 degrees. So with that we had a higher lift to drag ratio. We had a lower induced drag and higher lift to drag ratio. But provided the total span now with the sweep was the same. Like whatever the total wingspan is, it was just rotated in forward direction.
Got it. So unsweeping it was improving the vortex drag, and
Yes.
And you were also optimizing incidence while you were unsweeping it.
Sorry, what was the last point?
I was just wondering if while you were unsweeping the winglets, were
Yes.
you also changing incidence or exploring incidence as you were unsweeping it?
No. We just kept it by default, whatever it was. We didn't change.
Okay.
Yes.
It might be.
Yes.
So if that's an option you could exercise, you might want to take a look at doing that maybe at 2 or 3 different incidences, because as I go forward, yes, it will pick up more lift. So the winglets are working harder. And if it's reducing vortex drag, that means the winglets want to work harder. That's good. The question would be, if I had them aft, I'm not saying that we want them that far aft, but if I had them that far aft and I put more bite into them so they would toe in to load, that's another way I could load it up. I could unsweep it to load it up, or I could add more toe in to load it up, and they might have similar vortex drag benefits. It would just be interesting to see if that's the case. But yes, that what you say does not totally surprise me. And I think when we all look at this as a practical matter, it would clearly be really hard to keep that stiff enough for what we all want to do. So we probably need to unsweep in any case, some amount.
Okay.
So another point about the winglets, Mark, was initially we were instructed by Ron to place the landing gear exactly at the tip of the winglets. Handling wise, for some reason, I can't tell whether it's an X-plane thing, but I could not really maintain a good ground run when I had a tiny winglet at the wingtips. So I just placed it at the tip of the main wing. So horizontally where the main wing is, and I just have a vertical arm there. So I guess when if we happen to reduce the sweep, that might also help with the landing gear position, because since it's so far aft, we were not also able to take off, like do the takeoff move.
One thing that's for sure, at the point of liftoff, you might, that fore-aft position, since you can adjust the pitch attitude, you might not change the airspeed for liftoff, VLO. You might not change VLO, but it will allow the airplane to continue to rotate faster after liftoff, having the wheels further forward. If they're that far back, it's going to inhibit the rotation at liftoff. So I can see that. I can see that it would have an effect. And yeah, I think that makes sense. That I think you'll serve two masters by unsweeping that winglet, efficiency and handling, both. And then perhaps we could remerge, because it's very nice to have the wheels just integrated with the winglet, because then you have a natural fairing, you have a natural strut. It's real sweet in that way. Cool.
Yeah, and one thing that I wanted to ask, Mark.
Yes.
At this region where there is a connection of a wing and the body, we see some kind of kink on the lower surface. So what's
Yes.
that? Does that have any? I think I'm supposing that has a particular purpose, but we don't understand what it.
So yeah, you're right to be scratching your head. So let's look. So the intent ultimately is that those would be smoothed. And you've probably noticed if I have a lot of defining stations, I can move things. Sometimes I can move them a lot and I don't see a lot of change, right? You've sometimes perhaps have noticed that because if I'm changing something over, if the slices are close together and I change one airfoil, obviously it's not affecting as much of the area, and then the three-dimensional effects cause it to relax the influence in any case. So what we find is that even though the optimizer may make something that looks very, very particular, if you go over and fill it with Bondo and sand it, and fill it with body filler and sand it, you're going to get almost the same result as if the trailing edge is about the same. So my feeling is, could someone bring up a view and show me the trailing edge? Do you guys have an image so I could see the trailing edge on 4.1? You showed me something earlier where we could see it a little bit on the earlier in the presentation, or maybe the first presentation.
Slide number 5, I think.
Okay, that's pretty good. Yeah, so there, if you look at those, you can see that, okay, the trailing edge has a little bit of a feature, but it's not horrible. So as I march forward, obviously the trailing edge cutter condition is the most important element of what the airfoil is doing. So if I preserve that as I march forward, I can definitely slide airfoils up and down to help make a more unified center body. I tend to make it sort of flush across the top. Just depends on what you want. Sometimes when you have payloads underneath the airplane, it's kind of nice to have side area to work with. If you want to look sideways, put in a payload that's not just down. So I often make the top kind of continuous as opposed to having a hump in the middle. But both work fine. And if I look at it, you may find that you can straighten up the trailing edge a little bit by shearing the middle up. And if I look at the frontal view again, sorry, guys, there we go. Let's go back down slide 6. So I look at slide 6. Here's what would happen next if I were to say, let's evolve this airfoil system on slide 6. Could we go to that real quick? There we go. Almost.
There's a bit of a lag.
Yeah. Okay. So if I look at and scroll down just a bit so I can see 4.
Oops, sorry.
Yeah, it's zoomed in a little bit, I think.
I am struggling with PowerPoint for some reason.
Hey, this is all a miracle that we're having this discussion on the other side of the planet. I am ecstatic. Okay, yeah. So if I look at this, we can. My instinct would be to take the very center bit that's high and push it down low. That's going to fill in the divot in the lower surface. It's going to get rid of the hump on the top. So things are going to naturally smooth out quite a bit if I shear the airfoils so that they make a smooth shape on the upper surface. I think it's good. And usually you'll find that has a very small effect on the aero. And then even then you'll find that with all the airfoil stations we've declared, it'll be lumpy. And so what I have my guys do is once we have it and it looks good in the aerodynamic analysis, honest to goodness, I kid you not, hand on heart, what we'll do is, let's see, is there a way I can point? Let's see, maybe there's a way I can point too. Let me just take a look. Okay, I've got 3 dots up here, more stuff. Okay, yeah, report audio, no. Let me just see if
I
there's
think I
something
just
here.
let you.
Okay, can you see my
I
cursor?
think I just. Yep.
You see my cursor?
Not yet.
If maybe, let's see, I'm not sure. Let's see here. Yeah, I can't share my screen. That's all right.
Sudip, you
Maybe.
might want to just pull this up in OpenVSP so you can expose it to any planform view.
Well, it's okay. I was just going to
Okay,
point and yeah, what I was going to do was simply say that a technique that works amazingly well, and for all the academics in the room, cover your ears. Don't tell anybody. This is the truth. But once you shear the airfoils and get it kind of close, a trick we do all the time is we will take and we will make we'll take let's say the centerline airfoil and we'll go out past that first airfoil to between the first and the second airfoil, and I'll have my loft guy take a cut there, and then I'll have him take a cut between the next. Sometimes if we take cuts between the airfoil defining stations, throw away the original airfoils, you'll almost always start smoothing the surface. And yet, in a strange way, you're preserving the average effect. And sometimes you have to use a little artwork, but you can do some if you look at, yeah, okay, the cursor now it's between airfoil. If the center line is 1, then I have 2, 3, you're between 3 and 4. Imagine taking a slice between 3 and 4, a new cut in CAD, and then take a cut between 4 and 5. You can tell already those 2 airfoils look kind of like each other. They're kind of similar in position. And then I delete the airfoil in the middle and I will get a natural smoothing, but that airfoil has been informed by its 2 neighbors. So aerodynamically, it's a quasi-averaging of what's going on. And it's a very simple technique to make a nice, smooth surface that still preserves some of the most important elements of the airfoil stack. Yeah. No, there's this, even though it's very, very lumpy now, it'll be easy to make that nice and smooth and preserve the lift distribution that you guys have worked on.
Thank you.
Yep. Thanks, Mark.
Okay. Let's see what other stuff. So I also noticed in X-Plane, you chose to use 2 pusher motors. That gets rid of unbalanced torque and stuff, perhaps. Tell me more about that decision and if it's important or if it was just a discretionary choice.
I think initially I was basically just thinking about where to put the motors. And so that was going to decide how many, like whether I'd use one or two. And the reflex that we have at the trailing edge in both versions, I just thought maybe placing the motor around the reflex because there's a particular property we want to get out of it. I don't want to disturb that in any way. And so, moving sideways was sort of an intuitive option for us. And then how much sideways we go, dependent then on the diameter of the radius of the propellers. I think one specifically said it's going to be what, 20 inches, if I remember it correctly, Ron. But that's the number. Whatever number Ron gave us, that's the number we went with. And then with baseline 3 as well as baseline 4, engine is exactly at the same position. Still, I did not change that position. I think I only ended up changing the height of the engine with respect to the horizontal plane.
No, you're correct.
Slightly above the center of gravity now, and it's the span-wise location was determined.
Yeah, it's true that the flow at the reflex, obviously the back of the center body is working hard, is kicking the flow up for a lot of the trim, and so you would want to align it with that kick up flow, and you probably need to look at CFD to see what the flow relaxes at. It doesn't have to have perfect alignment, but you still could use it if you wanted to, but you'd have to be careful about aligning the prop. Yes. One thing that's nice about the prop at the back there is, I think we talked about this, maybe prop normal force. Did we talk about prop propeller normal force before? I think we did. But in any case, it can add some directional stability. It'll add a little pitch stability too. And if it's on the trailing edge of the center line, you can add pitch and yaw stability without shifting the trim point very much at all. You have that option anyway. So it's also, even though a lot of people in the drone world don't put the propellers on the nose, that still is a legitimate option. It has some consequences. The propeller itself is more efficient. It's not in the wake of anything. Of course, you're recovering some wake energy by putting the propulsor in the wake of the airplane, as you guys probably have read about, called wake recovery, wake pressure recovery. So you're putting the thrust back in where the drag was taken out, and that means that thrust minus drag can be set to 0 with less energy. So, but you can also do that mid-span. You still get some of those benefits mid-span. We've flown little UAVs with the prop on the nose of a blended wing, and you got to be really careful. I probably mentioned this before too. The upwash at the nose is a lot, so you might have the thrust line inclined down 20-25 degrees, and it seems crazy, but that's what it wants to be if you have it on the nose. Whereas on the trailing edge, it might be so close to 0. It might look sort of normal. And if you have winglets aiming down and wingtip wingtip gear, then you've got all the clearance you need if you want to put the prop in the back. It's kind of a nice package. Good. So is there anything else that you saw and I'm thinking especially as you were trying to fly the airplane in X-plane, let me ask you, Sudip, did you attempt any approaches to stall and stalls to see how the airplane behaved in stall?
Yes, so when we were just starting to fly baseline 3, I was not yet sure about how I was going to do the takeoff, and so we would in X-plane there's this feature of where you can just take your airplane up in the air directly, start from a particular altitude and a speed. And it was very surprising because whatever speed and altitude or whatever I would give, it would never stay in that position. It would immediately dive. or in some positions it would immediately like pitch up and stall immediately. And we thought that was maybe partly because when we are flying, we are always at a high angle of attack, and stall is very nearby. And so when we have, so for example, one place where I encountered stall a lot after I was able to take off and then fly up was when I was trying to trim it to a particular speed. So say if I want to trim to a speed very close to stall speed, it's how do I put this? Even if I was able to trim it, for some reason it chooses to just go for a condition where it just keeps losing speed very, very slowly. And then, so most of the stall that I noticed was not because it would keep pitching up, but for some reason it just kept losing speed. And
Got it. So
yeah,
it was kind of mushing. So it was probably doing an easy pitch up that was increasing drag, and your flight path went down. It just
yeah.
yeah. Okay. All right. And but it did. You weren't seeing a wing drop at the stall. It was just kind of mushy and tended to depart in a descent. So it sounds like it wasn't diving so much as just mushing. It was nosing up relative to the air flow, but its flight path was then going down. Got it. Okay.
Yes. And it enters a strange roll actually. So every time it stalls, it enters a massive spin. So you can't really recover in any way at all.
So it's so that's interesting because X-Plane does a pretty good job with spins. It's actually, because it's doing the blade element model, the airfoil stack model with the nonlinearities. If I see it spin in X-Plane, it's probably going to spin if we stall it right now. So what I'll be really interested in is to see how the new incidences on the wing have affected the stall pattern from tip to root. We normally want it to stall intentionally right at the kink of the airfoil. So right where the body meets the outer wing, we tend to want it to stall there. And if it stalls there, it generally will pitch down and it will keep the ailerons and elevons happy, and nothing on the outer tips will stall. Once one of the tips stalls, it'll spin and it'll happily stay on that spin forever. So we will want to take a look at that. And that might be, let's look at the slide 7. So actually, when I look at the twist change, I'm not seeing anything scary here. I mean, you've detwisted it, yes, but the twist of the outer wing and the twist of the mid wing are very similar. It's just on center line that you have a difference. So normally I would have said that DSN4 looks okay. I wouldn't expect its tip stall characteristics to change much. Obviously, the very winglet is doing something different, but that, if anything, should be favorable, I think. So anyway, it's going to be interesting to take a look at that. It might be fun in X-Plane just to arbitrarily add some more washout. Put like 3 degrees more washout in the tip and have it vanish by 40 or 50% semi-span. Just take the tip and untwist it some and start flying. Of course, it'll be out of trim, really out of trim. You have to retrim it, and then just see if you can help get rid of some of that spin propensity. I'd like to hear if that happens. If you see that, that would be very helpful to know.
Okay, yeah, I'll try that.
Mm-hmm. Yeah. And it might mean you might have to slide, if the airplane's still stable enough, you might have to slide the CG aft just a little bit to get it to trim, and that's okay. Just to do this experiment, that'd be fine.
So did you say slide CG aft, further aft from
the
the position?
Right. If your elevons are overworked, trying to trim out the change in washout. Now the washout, I take that back, excuse me. The washout should, pardon me, I'm saying it backwards. the extra washout should help it trim. So it'll bring the elevons down. So you should be fine. You should be fine. You'll have to probably put some uh, trailing edge down elevons in to retrim it, and that's okay. And then just do some approaches to stall. I would do, to exercise it, I would do some approaches to stall just straight in. I'm sure you're doing that already. And then I would do some turning stalls where as it stalls, it develops side slip. And then that'll really get it going and see if it has a spin propensity. And then do a before and after where you do some straight in stalls and do some turning stalls. And maybe always use like a, 30-degree bank angle and then just slowly stall, something like that. And take a look at if adding washout helps get rid of that spin propensity.
So just now, so when you're talking about the bank angle stall, right? So is that a standard technique we can follow?
Yes.
So typically we did
Yeah.
spiral test. So yeah, sorry, go on.
Yes. So the FAA and EASA and other certifying agencies, when you're certifying big airplanes, you do straight ahead stalls and you do turning stalls, or so-called accelerated stalls, because the stall happens at an earlier. So if at this condition my stall speed was 40 meters per second, here my stall might happen at 45. I'll stall earlier, so-called accelerated stall, because I'm pulling G. But the reason that they do it is not because of the G so much as they do it so that the airplane's in a realistic attitude, getting near stall, and when there's a stall break, when there's a G break, the airplane slides down the hill. It slides down this way, and that induces an immediate side slip. Without using rudder or anything, I suddenly get a big side slip, and that will expose whether or not there's a vulnerability to a spin departure or a wing drop or anything from that kind of asymmetry. So it's a nice consistent way to explore it, and it looks very much like what pilots might do or the airplane may want to do: landing approaches, banking and turning, and yes, it's pulling higher CL, so you're getting closer to stall, and it's a great way to expose issues.
Okay, yeah, we'll definitely try that.
Yeah. And I would also just take a look at, cut the sweep angle in half on those winglets, and maybe put the wheel on the winglet and tell us what you find.
Okay, yeah, we'll do that too.
Mm-hmm.
I should have grabbed my pen earlier. I feel stupid now.
Mm-hmm. Okay, cool. All right, guys. Well, this is good. I'm especially happy that you're in the X-plane phase, because it kind of helps you find, it does help you find things that will be a nightmare if we go to flight test. And we say, oh, darn, the airplane is too spin prone. Now what? So this is a great place to expose those issues. It's also great because you've been able to now look at what it's going to take to do a rolling takeoff. And I'm not surprised at all that it's like 1,000 feet. That makes sense. These airplanes, when you make an airplane designed for this kind of endurance, the field length often is penalized a lot, and which is also why these airplanes tend to be catapult launched so often. So that's good to know. But you've also got some handling information, finding out the issue with the far aft gear. So yeah, if we do a half and half, bring that winglet forward a bit, put the gear aft a little further than directly below the wingtip, see if we can keep that gear fixed to the wingtip. And if you say, hey, this is okay, I can manage this, then that's a good start. And then we can think about other things related to maybe what some people do. In World War II, if you look at the Oh, Ron, you know what I'm thinking of. The Gotha 229, or also called the Horton 229, was a flying wing. If you look at that airplane, they were doing a rolling takeoff from the ground. It has a huge nose wheel. The nose wheel on that airplane is actually the main gear, and the wing and the other gear are actually tail wheels. So there's two of them, but they're not carrying much weight. The nose gear is actually a main gear. It's a huge tire because it's carrying all the weight of the airplane. And it's holding the airplane at a very high deck angle because flying wings have difficulty in ground effect pulling the nose up that high. So it's all the same issues we're seeing, all the same issues. Some people, so we've tested 2-position nose gear when we've done takeoff things, a extended nose gear for takeoff and retracted halfway for landing. And then when you land, instead of landing and hitting, and right now it's still at lift equals weight, so a little bit of a bounce and it pitches up and it goes up, bounce and right. But if you take that landing gear, down a third even of that height, it'll stick the landing. It'll come down, and if you take it down a lot, it'll just go thud and just stick the landing hard, and it'll plant great, no bouncing. So 2-position gear is a possibility, or maybe like we were talking about, something that is extended that automatically retracts on its own after you get airborne. And then if it's okay, and then you get rid of the drag of the landing gear, of course. And as long as you have a nose skid or something, you can land that way. Anyway, lots of possibilities. And by the way, you could test that in X-Plane. You could make only the nose gear retractable, and X-Plane will drop and it'll hit the nose and it'll drag, and you'll see what happens. It'll be exciting. But anyway, it could be kind of cool. I can't remember how to declare the contact points.
It was only like,
just
for some
uses
reason,
geometry.
it was only the.
I'm sorry, Sudip, you dropped out again on us.
It had some weird issues. Sorry, I think my internet connection is really bad at the moment. Can you hear me now?
Yes. So
for some reason, when I try to make like a tail dragger type wheel, something very tiny at the wingtips, I just can't get it to stay straight on the runway. It just keeps yawing left or right, and it was very difficult to do the takeoff run. I don't know if it's issue with X-Plane or something.
Yeah, it might be an artifact of X-Plane, but for now that's fine to show the bigger wheels. That's fine because they should. Yeah, that should be fine. All right. Well, this is very interesting, guys.
Thank you very much.